All right, we are live. Welcome to another week of engineering design in Omniverse. I'm here with Jen, and I think we're ready to go. Actually, we're not because I'm not sharing my screen and I don't have anything open.
Yeah.
Let's do that. Let's see, share screen. Oh, I want the entire right side here. All right. Yeah, here we are. With Isaac Sim open, but nothing else. Let's open up JetRacer. And I got something fun to show off for you all today. All right. Let's just give it a minute. I don't want to show it off until we've given people a chance to roll in and join us. Some people have been following along with us for the last couple of weeks, and we don't want them to miss out on the cool stuff.
What cool stuff have you been doing though?
Oh, we got the simulation fixed, so it's running smooth like butter now. Really, really going smooth. And some of that was thanks to, some community suggestions that I had tried, but I thought, I should try these again, with now that I've got the community feedback. And so I tried, and that was mainly, you see these spheres around this. And then also I worked with some members of the Isaac Sim team to kind of nail down the simulation and get it stable. Yeah, so if you look, one thing that was really helpful is if you go to this eyeball, and you can go to show by type in physics and colliders. Boop. We can make our colliders visible. And I had these all set to be SDF meshes, which are pretty good, but they weren't good enough for these tires. They're just a little bumpy. And then they're way overkill for like these arms and stuff, where we just really need a bounding box or a simpler mesh, really. These are just these could be even oversimplified, because if you look, some of these bounding boxes, let's actually change it to selected only. That's kind of cool. Colliders selected. So if I select it, you can see that collision box doesn't fit it so great. If I was getting some weird collisions, that would probably be the first place I would look. This one, I changed this one to, what did I use for that? It's kind of a nice little, it's a little bit more accurate, isn't it? But it's pretty lightweight. What am I using there? Let's change this to the prim. Select it. That takes us all the way to the mesh. And I've used convex decomposition. Yeah, so like for this, let's see what that would look like. Just curious. If we changed it. Right now it's a bounding cube. Oh, convex hole, that would be even better. Bounding cube is really basic. Or you've got a convex decomposition. That's pretty lightweight still, but a lot rougher. So let's just go through these, right? We've got a bounding cube, which is really coarse, but really lightweight. You've got, I think next simpler would be, a bounding sphere if it's more of a sphere shape, but this is not. This arm is not. You got a convex hull is pretty basic, but you see it like nothing would pass through this open space. So a convex decomposition, it lets you have that open space. This is probably actually more of an alpha hull. So imagine if you took a ball and passed it around the thing. That's kind of what that would be more like. Triangle mesh, there you go. A little bit better. And then a mesh simplification. Let's look at that. I think that would maybe be actually a little bit cleaner than a triangle mesh, But in SDF meshes, it's given us the same thing for this, but I find SDF meshes to be pretty good meshes of objects like this. And so I'm going to switch back to bounding cube for now, because honestly, for what we're doing, we're only making contact with the ground. If that ever hit the ground, we'd be in a bit of trouble. You know what, though? Let's go ahead and I'm just curious how well this works. If we switch to these, if I go and I go filter by colliders. Oops, I took it off. Physics colliders. Now everything in here is a collider. So I can select just the colliders. I'll select this first one, and I'll select. These are all the colliders in the entire car. And if I, and this is going to overdo it a bit, but if I go to the refinement, sorry, where are you? The approximation, I can make them all convex decomposition, which is going to look pretty good for like most of my parts. But for these wheels and tires, that's too rough. And so then we'll just go back to just the tires and make those a bounding sphere. And I'm just going to double check that these rims don't poke out. Because what happened before is I made these wheel rims a bounding cube. I'll show you what that looks like. And the corners of the bounding cube poke out past the sphere of the tires. So when I was driving around, it was like kind of bumping. They were bumping the ground. So we'll change that back to a convex decomposition. Yeah, so the problems I was having the last week or two with crashes and craziness, I mean, it was really the way I was setting things up. There's a lot of detail to this that you've got to nail down. But I feel really good. Let's make all these visible now. By type, physics, colliders, make all visible. Yeah, that's looking pretty good. We've got the lightweight but semi-accurate meshes around our arms and all these steering components. We have the nice, we've got the cylinder we're using for the tire. I think this is great. And if we run the simulation, I don't know what I just did. What just happened? Oh, heavens. I'm just going to, I'm going to undo all that because I had it working fine. And that, let's see if it works now. Yeah, I don't know what, I'll have to figure out what I did there. But I've just gone back just for the sake of this live stream. I've got bounding boxes around all these parts, except for the chassis. That's a convex decomposition. And then for the wheels and tires, they're both bounding spheres. That way these wheel rims are inside of the tire colliders. All right, so let's take a look. Now if I connect my controller and I run, you'll see that my gamepad is still connected. Oh, I'm already on my chase cam. Let's just give it a better spot here. Hey, Denisco. Hey, Zia. Welcome. I can't see very far ahead. Let's get a better view. That seems like a pretty good view. All right, so now we're running our simulation. And look how smooth. And I can actually increase this max speed of this car a lot. The problem I run into is that it gets just kind of hard to control the car. I'm understeering now. So what happens here is I turn that wheel too much and it kind of it stops turning. But that's an actual real car thing called understeer, where your front tires are skidding. And then, but if I up the max speed, the rear wheels start to spin and I keep sliding out. It gets hard to control. So those colliders, that was one of the problems. So fixing those colliders made a big difference.
If you added friction to the tires, would it prevent it from skidding?
Yeah, it should. I wonder what my friction is like. If I go to my physics material here. So just as a quick explanation, I've got my friction's pretty high at 0.9 already.
Mm.
And if you drive a remote control car around in real life, what happens if you turn sharply with the throttle on? You skid, right? So I think it's actually kind of good that it skids. That, to me, that gave me some confidence that the simulation was working well. Yeah, and Zia says this rig looks so much better. I think part of it is having the colliders visible so that we know what's going on, right? And then, of course, it's running much more smoothly. Part of that is the sphere colliders on the tires are making it less bumpy.
And this isn't the full car yet either, right? This is just the bottom.
This isn't the full, yeah. Enough that we can kind of get it rigged up. Like I was showing you to the Isaac seam, and they're pumped because most of the robots they're rigging up, they've been doing with the physics car template, and which does probably a better job of doing an Ackerman steered car like this. But the problem is it doesn't translate into other types of robots very well. So if you want to do some other drive or movement type, or if you want to do a robot arm, then using the out of the box physics template, it gets you to the car quick, but it doesn't buy you any of that other kind of skill set or any of that other simulation. Whereas this, we're rigging up all of the joints from scratch. It's better. Yeah, right. Zia says, look, even at idle, we have joint rotation. Yeah, these shocks, right? They're killing me. Let's let's look at these joints. Let's look at
Are they not supposed to rotate?
No. I mean, they're spherical joints at the ends. And so ideally in the ideal joint world, they can totally rotate around that axis, right? But in the real world, you've got like rubber bushings in there that are really high friction and just don't rotate. But if you go to your shocks in your car, you could rotate them somewhat around that axis.
Ooh, I don't know why, but that just sounds wrong. I don't think I want to do that to my car.
Yeah, probably. Yeah, I don't know if I would mess with it, but let's go to the rear right shock. Let's go to the outboard and let's see what we got going on here. If we have joint friction anywhere. Yeah, I just put a tiny joint friction in there. I think the other thing we can do with that, let's put a limit on these. Oh, weird. And now none of them moving. Just kind of, let's try driving a bit. Yeah, so I just put a joint limit on this rear right one, which is the way that your real shocks are. They only have a small range of motion. Now it stops spinning. So let's do that for all of them now real quick. Shock front left and shock front right. Oops. Go to the properties and then advance. Here we go. Let's do like 10 degrees. which is honestly probably more than they need. Yeah. So now when we go, yeah, see they move around a bit. Watch it go. But then they stop. That's better. There you go. You kind of did skid.
So what's that part? That might be hard for me to point it out, but in the front of the car, when you're turning the wheels, there's this, yeah, like somewhere over there where it's just moving every time you turn the wheels.
That?
Yeah.
This is one thing that I think is really fun about this one. I'm going to take off the, let's see, collider view. There you go. It's actually harder to see, isn't it? I'll turn those back on.
Maybe
Right.
just do show selection.
Oh, yeah, that's a good idea. Physics, colliders selected. There's actually one right here, too. This is the servo arm. So when you have a remote control car, let me see if I can. Here it is. Here's my servo. And then here's my servo arm right here.
Right.
And then there's this link that goes across to the middle. There's this bar that goes to both sides. And there's two bars that pivot that go to the tie rods that actually steer the wheels. And my sizes are not correct on these, but here's the servo arm. Here's that link that goes to this center bar. And these two are rigged up with joints. If I go to show by tie physics joints, so you can see these joints here. And then those go into the end to these tie rods. So this has the same actual physics setup as the actual car for the steering.
Okay. Oh.
That's what you're seeing there. And so when I'm simulating it, where are you? I've actually have a joint drive on that servo arm. So I'm actually rotating this arm right here. It's like so Zia says, so this is rack and pinion steering. It's almost, right? It's servo RC car steering. A rack and pinion, for a rack and pinion steering is a little different. There's no rack and pinion here, but it's kind of like a modified steering that behaves like a rack and pinion steering, but works with a servo motor with the arm. So yeah, there you go. So the steering is actually simulated. I'm not just like moving the wheels directly. Have a steering linkage that.
Oh. So when you're moving the, I want to say GameCube, but it's not GameCube. Your Xbox controller.
Yeah.
It's actually moving that pin rather than moving the wheels because that pin is connected to the wheels.
Yeah.
Oh, that hurts my brain a little bit.
It's all right.
Then how does the reverse happen? So like if you want to go in reverse or forward.
I cheated on so with the drive, I'm just driving the four wheels directly.
Okay.
So
but
really,
turning is with the pin.
And I don't know if probably what I would like to do at some point, or would be cool, is in the real one, you've got the electric motor here that drives this whole gear chain. And it even has differentials in the front and back. And I mean, I ought to be able to set all that up with physics, but it'd be a bit of work. I haven't done that. Instead, I'm just driving all four wheels directly, which honestly, it's like with all of this, even with the steering, it'd probably be okay to drive the wheels directly. And it's fine to have not be all that accurate with our tire physics. It's fine to have it even be a little bumpy. The question is, like, how accurate does this simulation need to be? And if we're moving slowly, then it doesn't have to be very accurate. But if we want to train a car in Isaac Sim to drive fast, then it becomes important, because then, like, you need to train it. You need to have, if you're going, I don't know, 30 miles an hour around a corner, you want to train a car to do that, or RC car to do that, because that's really fast for an RC car, right? It's not so fast for a big car. If you want to train it to do that, you need to skid like the real car would skid, right? You need it to have you need it to perform very similarly to the real car. And I think with this setup, we have the potential to get there. Once again, with the physics car template, I think we could actually probably get there pretty well with the physics out of the box template for this Ackerman car. But then if we had other drive types, other robot types, it wouldn't translate into those, right?
Mm-hmm. So Zia's got two more questions. And then if we want, we can go over to containers.
Yeah. Okay, the servo does have gears, but you typically control servos by position. So with these servo motors, you have a voltage signal between 0 and 1, and 0 is or between -1 and 1, and 0 is you're pointing straight up, -1 is you're all the way to the right, 1 is you're all the way to the left, and 0.5 volts is halfway to the left, right? So I think it's just fine to simulate the servo just like this. I think it's this because we're thinking of what signal are we going to want to give this joint drive. I mean, that's the joint we're actually driving with the actual Jetson device, and the signal kind of corresponds. And no, I think I would stick with. I wouldn't model the internal servo. I think that would be. I don't think that would bias anything kind of ever, but I could be wrong. All right, and then so I wonder if the differential will make a difference. So it will totally make a difference at high speeds, because the way these are both open differentials, and what that means is if as it's going around a corner right now, I'm not sure exactly how it's behaving, if tires are skidding or that sort of thing. But with the differentials help it not skid around corners. But they also have this drawback of where if you do start to skid because you're driving fast, then whatever wheel is spinning or is not getting traction, with these types of differentials, these low performance differentials, all of the power from the motor will go into that spinning wheel. And that starts to give you some poor performance behavior at high speeds. And that's why fancy sports cars they'll have different types of limited slip differentials. That's why rock crawlers have lockers. It's to give a high performance vehicle, the right kind of differential characteristics. Yeah. So, okay. So there we go. Oh, there was one more thing that I had to fix. And this was just a hunch, and it was totally right. If you remember right, it was bumpy, and then the bounces would get a little big, and then it would crash, right? Because the bounces would get bigger and bigger. And I thought the bounces and the jitters seemed a little big even for the SDF meshes on those tires. And I was totally right. I looked at this. Let's talk about this for just a minute, and then we'll get to containers. If you look at this collision group right here, what it does, and let me show you this by type physics. Well, let's stop this actually. By type physics, let's turn off the joints and turn on the colliders. If you look at the colliders in this remote control car, they overlap. A lot of them do. And with our rough approximation methods, we kind of like it that way, right? We don't want to have to measure everything so perfectly that two things that are joined together can't overlap, or we don't want to measure the actual real friction by contact. We want to just, idealize that friction by modeling the physics joint. And if two parts are joined, we want to say, you two just don't collide with each other. And really, all we care about is we want to make sure that the car collides with other things like with the ground, or maybe if we put an object into the scene, we want it to collide with that scene correctly, or that object correctly. That's what we care about. And so we just want to put a filter in that says to all these parts that are part of the car, don't collide with each other. And that lets them overlap without wildness going on. Because what will happen is, let's say that you have the shock here and the chassis or in this arm overlap. If we had colliders on for those, we would have a joint saying, okay, shock, you want to be here so that the joint is satisfied. But then the colliders would say, no, you need to be over here so that the collision is satisfied. And if that joint and that collider are fighting with each other, that's when we get those crashes. And in particular, if we had some parts that weren't overlapping, but then under just a little jitter, they did start to overlap, we get some really nasty numerical problems. I'm pretty sure that's exactly what's happening. And the reason that what I did is I just figured, I must have missed one or some of these meshes when I was putting this together. And so I just took this collision group, which says, the collision group says, I want to have all of these colliders in this group. And then if you filter the group against itself, it says, I don't want this group to collide with anything else in this group. And they ignore each other. And so, yeah, that's what they do. And then, and I must have missed one. And so there was some nasty collision going on. So all I did was I deleted all of the colliders from this group and re-added all of the colliders, making sure I got all of them. And I haven't had I've had some physics glitches here, but none that crashed Omniverse since then. And so let's just one more time, let's see this thing in action. And then let's answer some questions. Okay, so here we go. Yeah. So really smooth. No more problems with those collisions. You can see, this is kind of fun. If I turn right and left, you can see the suspension moving. Oh, and of course we get a crash. I've got the magic touch. What can I say? Oh, it didn't crash though. Yeah,
it
there we go.
Clipped out of the world and then just
yeah. I'm being kind of crazy with it, so I just like seeing that suspension articulate as you steer right and left. It's just kind of, I love that. Let's see. This is really cool. See, I'd like to stick a Tesla model computer plus a Jetson Orin into a mini Tesla truck and have Omniverse be able to train the mobile PC to either follow, lead, carry, or be a skateboard mode. Yeah, I think, we don't have, if you mean like the Tesla AI, like self-driving model, I'm afraid I can't get that for you. But you can certainly train your own model and do the Jetson Orin. Yeah, I think that's a cool idea. I think getting a Tesla, if you use the TT02 for your setup, then you can certainly follow along with what we've been doing. I haven't screwed it down yet, but I've got a Jetson Orin right here that is everything except for just final 4 bolts. I just, I actually cleaned my office the other day and put away my Allen wrenches. And now I have to go get them again before I can bolt it down. That's what I get for cleaning my office, right? And then, yeah, let's see. Okay, I'm just wondering, why do we have so low FPC on Isaac Sim, even though a frame, do you mean frames per second? Let's see what we're doing. 54. Oh yeah. 18 frames per second. You know, that's a good question. I'm getting, you know, kind of a low frame time. I can dig into that a little bit. I probably have some settings that aren't great, or I think a few other things as far as scaling that up. I'm going to guess that there's some overhead with, I mean, we're doing some very accurate physics simulations with articulations here. And one thing you can do, we're actually displaying the graphics. And if you really with Isaac Sim, I would think of this as a debug window. Okay. If you're going to actually do some reinforcement learning training, you will be using Isaac Gym, and you will not have this displayed. And Isaac Gym will just, it won't display the graphics. It will compute graphics if it needs to get to visuals to those robots. But you can, it'll just go as fast as it needs to get everything done, or slow. So it doesn't need to be in real time. It can be faster or slower than real time as needed. And you can spin up any number of instances at once, and which is a bit of a good segue into our next topic, which is containers, because containers are really a big part of how you do that. But let me make sure. Yeah, what other questions do we have? Let's see here. Just going through some comments here. Yeah, this is a good comment. It looked like a crash when two tires were off from viewport. Yeah, and one thing I found, sometimes what will happen is especially where I'm steering back and forth, sometimes that physics solver will like try to flip an arm 180 degrees or something like that. Which if you know the math behind it, you know, it's like it can be tricky. Those are really common edge cases where things will kind of want to flip the opposite direction. It's like a positive versus a negative sign. And one thing that really seems to help is adding joint limits to some of these joints, so that the solver knows without a doubt that it can't flip over the other way, right? I had that with the front tire. When I first switched to spheres, it was really stable, but there was this numerical error where both wheels kept like flipping out 90 degrees, and that was breaking the steering. Like the steering was all messed up, and it was messing up the simulation. But then I added joint limits to that front steering, and it hasn't been a problem since. All right, so let's talk a little bit about containers. And I think I'm new to containers myself. Jen, I think you're also not so familiar with containers. Is that right?
Not an Omniverse.
Okay. Where have you used containers before?
Oh, gosh. Long ago, back in 2016, 2017. I was working with my professor, but that was when we did really weird things.
Okay, fair enough. So I think a lot of people are familiar with the virtual machine. Yeah, I know. Zia says we are going to need Papa Chuck. And of course, this is the one day he doesn't show up, right?
Somebody at him in the Discord.
Yeah, get him over here. So I think a lot of people are familiar with, I think we're familiar with our computers, right? Our physical machines. Your physical machine has, so much RAM, it has so much hard disk, it's got a given GPU, right? And that's your physical machine. Now we can abstract that into virtual machines. So if you have, this is typically, you can do it on your local computer, but it's typically done on like a server, in a server system, is where you'll have a really powerful physical machine. And then what you'll say is you'll create virtual machines. In a virtual machine, you say, given that physical machine, let's say we want to take one physical machine and turn it into two virtual machines. Then you would, there's probably a little bit of overhead for whatever's managing your VMs, but ignoring that, you would say, okay, of my RAM, we're going to give half of it to virtual machine 1 and half of it to virtual machine 2. And we're going to take our disk space and we're going to give this much to VM1 and this much to VM2. And you're going to go through and you're going to allocate those resources and you're going to assign them to your virtual machines. And those resources are reserved. You can flip them around, but it takes some configuration. Yeah, but so it's essentially like you're creating a physical computer, but you're just kind of assigning those resources to be used, and they're reserved. You can't really flip them around so easy. And then also that virtual machine, it's either, say, a Windows or a Linux machine. And if your kind of your physical computer, if that actual original physical computer changed operating systems or something, you could run into trouble. So it's kind of, maybe you kind of have to set up that VM on that physical machine, and then it exists, right? So people wanted a way, say, hey, we want to be able to have something like a virtual machine, but even lighter weight. We don't even necessarily want a whole operating system. We just want the bare bones of what you need. We want it to be really easy to spin it up. Oh, and by the way, when you turn on a virtual machine, it's actually booting the operating system and going through all that work. So it takes a while to boot up a virtual machine, just as long as it takes to boot up a physical machine. And they said, we want these, and we want it to be just the bare bones you would need to run a single app, right? So let's say you have an app, and say, what's the bare minimum you need to run that app? We want to be able to run that app on any operating system. We don't want to have any installation instructions. We just want to be able to like spin it up really quick and easy. So how would you do that? And the answer is with containers. And with a container, what you're essentially doing is you're saying what operating system you want to use. And they're typically done in Linux, not always, but the reason that is because Linux is open source, people have come up with Linux distributions that are just really, really lightweight. They don't have anything extra. And so you can have these full Linux distributions that are like 100 megabytes. They're just really bare bones. And there's just all these flavors of Linux that you can pick to cater to exactly the app you want to run. Just what you need. No more, no less. Okay, so you kind of pick the bare bones of operating system you need. You pick any libraries you need, any files you need, and you just set up all these files, and you describe kind of what does this setup look like, and you compile it together into a container. And that container, it has the operating system, it has all the dependencies, it has everything. And so it's a completely contained, portable application. And
there he is.
There you go. Yeah. I'm not sure what he's saying here, but I don't know. What does PCIO mean? The input output communication. So they all run in Linux. I don't think that's true though. I think you can have a Windows container, but I think most people do Linux containers. And I think that's kind of the way to go. Papa Check might correct me, but yeah, so that container, it's a bundle of everything you need. And then you have, I think the most common is Docker. Docker is a container, as an application that runs containers, and you can install Docker on Windows or on Linux, or I believe even on Mac. And then it does run on Mac. That's right. And then you give that container to Docker, and Docker will like spin up that OS and run that application for you in this container. And as far as you're concerned, it looks like it's just running the app. You don't see the OS in the background. You don't see any that stuff in the background, unless you're explicitly asking it to run the OS. But and then yeah, and PapaCheck is, yeah, Docker is not the only runtime for containers. There are others, but Docker seems to be the most common that I've seen. And so Docker, or your whatever's running your container runtime, can kind of spin up that container really quick. And that's my description of containers in a nutshell, from a non-container expert who is learning about containers. And the reason, and I'm recommending, if you are interested in robotics, I think that I'm now on board that you really ought to learn about containers. And the reason is, as I'm getting more into machine learning, what I'm learning is that containers are the most common ways for people to deploy, or I got to be careful what I say here. Containers are a very common way for people to deploy AI models. So they put them in a container and they hand over a container. And the same goes if you want to write a program for an edge device, such as a Jetson. People are doing that with containers. And it's really, let's see, what else have I run into? If you want to use robot operating system, ROS2 applications are often containerized. And so if you want to have, and the reason I think people are doing that is because, and I think it's especially good for us, is because we're going to be training this thing in one environment, and we'll be deploying it on the Jetson in a completely different environment. And great comment from Zia. Containers allow us to freeze our dependency libraries. Absolutely. So you can create a container for one app that has one version of dependencies, and you can have a second container with a different version of those same dependencies, and those can run side by side on the same computer without any trouble, because you're not installing the dependencies on the computer, you're deploying them in the container. So they are completely siloed, don't touch each other, don't interfere with each other. Yeah. And let me see here. Can I actually distribute all of the work for an application across a cluster of containers, like logic in one, physics in one, in another, etc.? I believe so. And this is where I'm learning, right? I think you might want to have, let's say you had multiple AI models. Like, let's say you had one AI model that was controlling the drive of this car, and then we attached a robot crane arm onto the top of the car, and you had a separate AI model that controlled that crane arm. I think we could have those each be a separate container that are talking to each other. And they don't even need to talk to each other. They could each be running on the Jetson at the same time as separate containers. I think this is what I'm. Yeah. So I think that's how. So I think what we could do is we could write one template here in IsaacSim that gets our RC car, this Ackerman robot. That's the more technical term, to move around and drive like we want it to, and we can have a completely separate template that just trains a little crane arm to pick stuff up, and maybe it's got a grabber, I don't know, and do some other tasks. And then I think we could deploy both of them and run the two containers simultaneously on the Jetson, because you can run containers are like little bundled apps, And I think we could run both containers on the Jetson at once. Great comment. So yeah, I think we can use the containers to kind of train discrete parts of our tasks and get them to work together. Now that said, I believe that's kind of what ROS2 does, is it lets you train the different parts of your robot and then bundle them with logic. And that might be a better way to go than to have the separate containers, because remember, each container does have its entire operating system. Like each container will have starts off with like a Linux operating system, and they're absolute bare bones operating systems, don't get me wrong, but I could see that becoming a bottleneck on the Jetson if we have a lot of blocks. So there's a lot of architecture to figure out here. I do not have the answers. I just at this point, I'm very confident that containers are a big time, containers are a really big part of that solution. And so I think that my goal is to become fluent in containers here. Yeah. And what else about containers? Yeah. So Docker connects the native machine operating system to the container. Yeah, that's right. And what I've learned is it doesn't do that at the OS. It doesn't do that at like the OS API level. It does it at the OS kernel level. So Docker is working at a very low level with your operating system. So it's very performant, which is totally cool. It's so cool. Yeah. So you're basically, yeah, I think it's really cool. Yeah, let's keep talking. I mean, what are your questions about containers? And I want to hear what your thoughts are. Ross sends real-time messaging. Just a second. Oh, so here's the question: is can containers talk to each other? As far as I know, they can. I do not know how that works. So that's high on my to-do list. And there are a few questions about ROS. I have not dug into ROS2 yet. I haven't gotten that part. And I think part of the I'm just having a discussion with Isaac's team if we want to use ROS2 or some other architecture, which I don't understand yet, but I think it might be having us coming up with a basic way that containers kind of talk to each other. Here we go. Great comment from Papa Chuck. Containers need an orchestration software to talk to each other. The simplest is Docker Compose. There we go. Cool. Yeah, there we go. And then Kubernetes. That's another way to orchestrate multiple containers. And a lot more from what I understand. Like Kubernetes lets you automate the creation of containers. It's like a scripting language on top of containers that lets you build, deploy, like all sorts of work with containers. And a lot of people commenting on ROS. And so this is where so there are these different groups in robotics, these different camps, if you will. You've got your more open source maker camp, which is where a lot of us are right now. And ROS2 is very popular in that group. And then you've got your robotics researchers. And my understanding is that your academic researchers are also big fans of ROS2, which is great. And then we've got our enterprise folks. And my understanding is that the enterprise folks are still not completely on board with robot operating system. And the trouble there is that there's only one of those that's going to pay you guys to do work. And that's the ones that are not completely on board with ROS2. And so I'm kind of talking internally with Isaacson folks, trying to figure this out, because my goal is to come up with a clear path to monetization for you. And if using ROS 2 is going to be a roadblock to you making money, then we're just going to have to go a different route. And I hope you all are on board with that. But my hunch is, and my gut feeling is that the people who are going to pay you, like if you are working with a big robotics company, yeah, I think they're going to care about your implementation and your architecture and stuff. But like I've been working with this company, Hypercraft, right? I've been working with this Hypercraft company, and they don't care how you do it, right? They're going to have a task like, hey, we want to do reality capture once a day. Or, hey, we want to move this cart from point A to point B without hurting anyone. And we want to go through a space that has people, right? Because we can't do this fancy factory that has dedicated lanes for robots, right? We just got to have them in the same space. So, and they don't care how you do it. They just care like how much it costs, right? And especially if you can get these tasks down to where you can do them repetitively and okay, to train a robot to go from A to B in this kind of a space, it's going to be one of these 5 robots, and I can narrow it down to how long it'll take me really easily. I know this space really well. So if you can get to the point where you can give them a flat rate cost of, if this is the task you want to do, it's going to cost you $5,000 for me to do that, and have a robot on site that does that, or $10,000. If you can give them a flat rate, I think that there are a lot of mid-tier customers you can get at that level, and that's what we're shooting for. Because I want you guys to make, I don't know, $3,000 to $5,000 per job, because if you can do that, if you can get customers where you're making $3,000 to $5,000 per job, if you can get like a customer a week, or 2 customers a week, and start pumping these out, then you can make a living at it, like a really good living at this. That's my goal, is to find that niche where you all can find 100 customers that are going to pay you a few $1,000s each per year, so you can make your living, right? Okay. So, well, like I said, if ROS is helpful for that, great. If ROS is a barrier for that, we're not going to use it, right? We've got to make money. Let's see. Yeah, okay. ROS is easy to learn concepts, but it's not so good. And although I have heard that ROS 2, like I've heard that ROS 1 was really, it's like, these neat concepts, really great in theory, but just didn't work very well. But I've heard that ROS 2 was a lot better. And I've heard that some pretty big research labs are using ROS 2. Oh gosh. That's interesting. Well, I don't know. So the Amazon spots may use ROS. Oh, some? Yeah, I don't know about that. I can neither confirm nor deny there. Don't know. That's not. So Zia is saying for drones, I need ROS. That's not true. Come on. You don't need ROS. I mean, it's just, ROS is just a tool, right? Like I love myself a good Sawzall, but if I didn't have a Sawzall, I could still tear down a wall. I mean, it just take a little longer. But in this case, yeah, it's a tool. And the thing is, the other tools in our resource are like Python and C++. And I know we can do it with Python and C++. Guaranteed, right? Those tools can do anything. It just might be a lot of work. And so the question is not, do we need ROS or not? The question is ROS going to speed us up or slow us down? And in the measurement of speed us up or slow us down at what? Speed us up or slow us down at making money. Because even if it can speed you up at training a robot, and you go to sell some services around that robot, and someone says, "Oh, you use ROS 2." I'm sorry, we're an enterprise company and we can't use ROS2 because it doesn't have support. If that's the case, and whereas if you had your own code base that was written in C++ and you said, yeah, I sell enterprise support for that, so we can use it. And that's a real thing. That could be a real roadblock. And so, if ROS2 is going to be if ROS is going to be a roadblock, we're not going to use it. If it's going to help, we're going to get together and write whatever libraries or architecture we need instead of ROS2 if ROS represents a roadblock. So there you go. That robot operating system. But like I said, I have heard good things about ROS2. Definitely going to dig into it. We got 5 minutes left. Jen, thoughts?
Well, have you discussed how it relates to Omniverse and OpenUSD?
Containers?
Yeah.
No, because I don't exactly know that. But I think, and my hunch is that we're going to have containers running in Docker, and then we're going to write some sort of an extension that allows that container to communicate with Omniverse. That's my guess at this point. Just, I think, a pretty good guess, but I don't know what else would we do, right? But we got to write extensions. That's what we do.
So that means that in order to find the answer, you're going to have to hop on our Discord to keep up or add these events to your calendars.
Yeah.
To hear
true.
more, right?
Yeah. Absolutely. And then, and I was just going to say, I think another reason that these containers are so great is because we're going to be able to develop a container on our local computer, run it on your local computer, and then deploy that container directly to a Jetson. And it should run with the same resources, same as is. It should, as long as it's a container that fits on the device, resource-wise, should be good to go. Should run the same. Yeah.
I wonder if you can work with Renan on getting all that stuff set up.
I'm working with a bunch of people. Yeah, there's a host of people helping me get these containers working, and with Isaac's team's they're really helpful. And it's just at this point, it's kind of limited by how quickly I can learn some of this stuff, which is not nearly as quickly as I wish it was. It's a whole new domain for me. I've never worked with containers before. Well, that's not true. That didn't count though. I was doing some web development, and I used Visual Studio can automatically, if you're doing a website, it can automatically containerize it and run it and debug in a web browser. I did that, but all I did for that was install Docker and then debug and choose that option for debugging. I didn't actually author any containers. But this week, there's some really cool stuff online. I watched a YouTube video. I've built and deployed a Docker container. I've done some. I'm learning my Linux command line stuff. I'm not even a Linux user. I've got to learn Linux command. A Linux command line is like the language of Docker. I think it's kind of bread and butter for working with containers. So learning that. Luckily, when I was a kid, we had a Commodore 64 was our first computer. And then my dad bought an IBM compatible when I was like 10 years old. And it came with Windows 3.1. And he had never used Windows before. So he's like, what is this Windows thing? So he just uninstalled it, and we used DOS command line on that computer for everything. But all I really did was move files around, launch Paint to draw like little images, and there's this game Captain Comet that I would launch. So, but I did some basic DOS command line over the years.
Good stuff. So Zia wants you to document all your learnings.
Probably should. I'm trying to think of the best. This is a great comment. Okay, there are two difficulties. One is it slows me down, but maybe that's okay because maybe if it slows me down, that's okay. But if we're working together, it would speed us up as a collective. The other, so maybe I should probably do that. I should probably be more active. The other problem, two more problems. One is that I keep going into lots of dead ends, and I feel bad taking everyone into a dead end. Like if you followed along with my week, you'd be like, okay, this guy is all over the place. Like it's just like dead end, dead end, dead end, and then a path that progresses. And then the other problem, which I think I can work around, is I'm working on some internal NVIDIA projects that have to as I go that I can't share. But I think I can just let's slow down and document as we go. And that could even be as simple as talking to you all more on the JetRacer channel about what I'm doing and what I'm as I learn.
Yeah, I mean that's a start for documenting. Maybe just like throw in like, hey, I learned something really cool, and just throw it out there.
Yeah, Zia, do you want to? What solution would you use for the documentation here? What technical solution or what architecture? Like, where do we just post stuff in Discord? Do we have a wiki? Do we have a Google Doc? I don't know what Sphinx is, but we can do that. What is Sphinx? Sphinx. That's what he said. Okay. And what's do you just have like a markup docs, or I guess we'll just I'll look into Sphinx a little bit here. We'll find out what Sphinx is and get something going. Is there like a free hosted Sphinx solution? Yeah. Oh, and he mentioned and Papa Chuck mentioned the Seattle Robots Lab. And by the way, the Seattle Robots Lab, they use ROS too. I've learned they're the biggest ones. I was thinking, no, we can't use ROS. It's a roadblock because the enterprise folks don't like ROS. But then I heard that the Seattle Robots Lab is using ROS too. And you know what? And you know what I should do? I should ask if one of them will join us on this live stream. And I can get somebody from Isaacson for sure on the live stream. So let's start to do that. Maybe let's get some subject matter experts from around NVIDIA because we have a lot in these different areas. I could get a container expert. I could get a robotics expert. I could get an Isaacson expert, and I'll work on lining that up. And I'll also look into Sphinx and start participating more on the JetRacer channel when it comes to my progress. That's the end of our live stream.
Mm-hmm.
All right, y'all. Let's keep on keeping on. I've got a lot of assignments. Let's talk about it more on Discord, and maybe see if some of you if you could set up the JetRacer or the Sphinx thing for us, that might be better because I'm getting overloaded here. But let's talk about it more about JetRacer and on the JetRacer channel and get that going. Until next week, have fun and please share what you're up to on Discord. I don't want to see what you all are doing. So have a good one, everybody.